We are on page 39 today. We're going to take a look at our exponentials and logs, finding inverse functions or exponential functions and log functions, and then we're going to take some time to look at some more graphs for our log functions. So finding the inverse, okay, this was in your notes from last night. When we're finding the inverse, we're going to start by swapping x and y, okay? So the notes that you watched over this looked at just finding inverse of logs or inverse of exponentials, but we did some work earlier on finding the inverse for any type of function, and we know it always starts by swapping x and y. So that's where I'm going to start with number one. I'm going to swap x and y. So x equals log base 9 of y. Okay, I'm going to start there. And then my goal is to get y by itself. Now, when I had something like x equals y plus 2, we would just subtract 2 to the other side. Or when I had something like x equals the square root of y plus 4, I knew I had to square and do some things like that. When I've got a log, we want to rewrite it in its exponential format. Before I can do that, I have to make sure the log is by itself. So I'm not adding or subtracting anything outside of the log. I'm not multiplying the log by anything. For number one, we do have the log by itself, so we can go ahead and rewrite this in its exponential form. So the base for our log becomes the base for our exponent. The log is equal to the exponent. And then the argument is what that exponential function is equal to. So my inverse function here would be 9 to the x equals y. Since y is by itself at this point, we're done. That's the inverse function. Okay. Now we're going to do this again. For number 2, we have a log again. We want to find the inverse function, so we're going to start by switching x and y. So I get x equals log base 1/4 of y. I want to get y by itself, so that means I'm going to have to rewrite this in its exponential form. Again, the log needs to be by itself. It is by itself here. I'm not like adding 2 or subtracting 7 or multiplying by 5. So since the log's by itself, I can go ahead and rewrite this. The base for my log becomes the base for my exponent. Since this is a fraction, I'm going to throw it in parentheses. My log is equal to the exponent. And then the argument is what the exponential function is equal to. For number 3, we have an exponential function this time. I'm going to start the same way. I'm going to switch x and y. So x equals 5 to the y minus 1. And now I want to get y by itself. Since we're starting with an exponential function this time, we're going to have to rewrite it in a log form. So I start with one, I end with the other. But this time I've got something else over here. I've got this minus 1. So before I can rewrite it, I need the thing with the exponent by itself. Anytime I'm rewriting, I need the log by itself, or I need the thing with the exponent by itself. So that means my first step here is going to be to add 1 to both sides. So I get x plus 1 equals 5 to the y power. And now I can rewrite this in log form. So the base for my exponent is the base for my log base 5. This is the argument of my log. Since it's not just x, I'm going to put it in parentheses. Tells me I'm taking the log of that whole thing. And then it's equal to the exponent. Now y is by itself. So we're done there. That's the inverse function. I want you to try 4, 5, and 6. Try 4, 5, and 6. remember we start by switching x and y. And for each of these, we're going to have to rewrite it in its alternate format. Another minute or so and we'll take a look at these together. Okay, for number 4, first step, switch x and y. So I have x equals 1/4 to the y plus 2 power. Since I have something in an exponential format, I'm going to have to rewrite it as a log. My exponent here is a little more complicated since I've got the y plus 2, but that's okay. All I have on that side is the thing with the exponent. So even though the exponent's a little messier than what we've seen so far, that doesn't matter as long as I've got the thing with the exponent by itself. So I'm going to go ahead and rewrite this. This would be log base 1/4 of x equals our exponent, y plus 2. Now remember, we want to get y by itself. That means we have one more step here. I've got to subtract 2 to the other side. Now, when I subtract that 2 over, it's just going to stick here at the end of my log. It doesn't go inside the argument. It doesn't impact the base. All it does is hang out at the end. When I evaluate this for a given value of x, I'll evaluate the log first. Whatever that number is, then I'll subtract 2. Questions for me on number 4? Okay, let's take a look at number 5. This time I've got ln. Remember, that's natural log. That means the base for my log is e. So I'm going to start the same way, switch x and y. So x equals the natural log of 6y. Since I've got a log, I have to rewrite this in exponential form. So the base is e. Since we've got a natural log, that means the base is e. So this would be e to the x equals 6y. Since 6y is my argument. I want y by itself. So my last step here is to divide both sides by 6. So I would get e to the x divided by 6 equals y. That's my inverse function. Questions on number 5? Okay, for number 6, we're starting again with a natural log. I'm going to switch x and y. So x equals the natural log of y minus 1. Since this is in parentheses, that means y minus 1 is my argument. So I'm not going to touch the 1. okay? It's in the argument because of those parentheses. So I'm going to go ahead and rewrite this. Again, natural log has a base of e, so this would be e to the x equals y minus 1. My last step here to get y by itself is to add 1 to both sides. So I would get e to the x plus 1. Notice that's not part of the exponent, equals y. Questions for me? Okay. So again, we've seen inverse functions before today. These are specifically inverse functions working with logs and exponentials, but they work the same as the inverse functions we saw earlier. Switch x and y, and then get y by itself. The biggest difference here is we're swapping forms to be able to get y by itself. The next thing I want to look at are some graphs of our log functions, okay? Now, at this point, we haven't really talked about what it means to evaluate a log or even how we do that. We'll get to that. So for right now, the tool we have in our toolbox to be able to graph a log, okay, to be able to plug values into something, is to rewrite it in its exponential form, okay, which is what your notes showed. So that's what I'm going to do here. So I want to be able to rewrite this in its exponential form. So starting with number 7, the first thing that I want to do is figure out where my asymptote should be. And we know from our notes that instead of a horizontal asymptote like we had with our exponential functions, we're going to have a vertical asymptote here. Its default spot is at 0. If I move left or right, that would also move my asymptote. So if we take a look at number 9, I've got x plus 4 in parentheses. That tells me that my asymptote is going to move to the left 4. But if I take a look at number 7, I don't have x in parentheses with anything. So there's no shift left or right here. That means my asymptote is going to stay right at 0. So just like when we graph our exponential functions, I want you to do the asymptote first. Okay, get that landmark on there. That will help you as you're evaluating for more points to make sure that your points are reasonable. So we know that all of our points should be to one side of our asymptote. They should be over here. Okay, so if I've got stuff that lands on the other side and I've got points on both sides here, that tells me something's off and I should go back and double check my work. It's like why I like to put the asymptote in first. Now that I've got the asymptote in, I'm going to go ahead and rewrite this in its exponential form. I'm not going to go completely to the inverse. I'm just going to rewrite it in its exponential form. So in order to do that, I need the log by itself. So I've got to move this 1 to the other side first. That would give me y minus 1 equals 0.5 times the log base 2 of x. Now I need to move this 0.5 to the other side, so I'm going to divide it. Dividing by a half is the same as multiplying by 2. So just to avoid some confusion, I'm going to write this as 2 times y minus 1 equals log base 2 of x. And then the last thing I'm going to do is swap this to its exponential form. Okay, that's why I've been doing all this moving around so I can rewrite it as an exponential function. The reason I want to rewrite it as an exponential function is because I don't know how to plug in values for log right now. We haven't talked about that. We will talk about it, but we haven't done it yet. So again, I'm using the tools that I have in my toolbox. So my exponential will have a base of 2. Here's my exponent. So I'm actually going to go ahead and distribute this in. This would be 2y minus 2 equals x. Okay. And then here's where things are going to get a little weird. Okay. Normally, we pick values for x and plug them in to see what we get for y. Doesn't make a ton of sense to pick values for x right now and then try to figure out y. So that's not what I'm going to do. The easier place to plug in numbers right now is to plug in numbers for y. So I'm going to pick values that will make this easy to evaluate, but I'm picking values for y. Okay, that's goofy. That's different than anything you've ever done when you've been graphing functions. So I want values that make sense for y. So I want things that are going to give me an easy exponent when I simplify. So when I say easy exponent, I mean things like something to the negative first power is usually not that bad. Okay, so something, whatever it is, or something to the 0 power. I like when the exponent is 0 because that just simplifies to 1. right? No matter what it is. I also like something to the first power. That's not too bad. And something to the second power is usually not terrible, although some of our numbers when we square them can get kind of big. So if I had like 5 squared, that's going to be off my graph. So I try to stick with these 3. And I'll throw in a square sometimes if that's a reasonable number too. Just like when we're graphing our exponential functions, I want you to graph 3 points as well as the asymptote. I want 3 points from you as we're working today so that we can see the shape of our graph. A lot of times we struggle with what the shape of the log graphs can be after spending so much time graphing those exponential functions. The more points we have, the better picture that we get, the harder it is to give me something crazy on your coordinate plane, okay? So I want to pick a number so that when I simplify what I've got right here, I get an easy exponent. Well, if I plugged in 0 for y, I would get 2 times 0 minus 2. So I would get 0 minus 2, which is negative 2. Negative 2 is not the easiest exponent. Maybe I don't want to plug in 0. If I plug in 1 for y, I would get 2 minus 2. That's an easy exponent. So I'm going to plug in 1 for y. Okay. When I do that, I get 2 times 1 minus 2 in my exponent. 2 times 1 is 2. 2 minus 2 is 0. 2 to the 0 power is just 1. So if I plug in 1 for y, I get 1 for x. I'm going to do this again. I'm going to try to pick another value. If I plug in 2 for y, so I want to pick stuff probably close to 1. If I plug in 2 for y, 2 times 2 is 4, minus 2 is 2. 2 squared is not terrible. So I'm going to plug in 2 for y. So this would be 2. My exponent is 2 times 2 minus 2. 2 times 2 is 4. 4 minus 2 is 2. 2 squared is 4. That's not so bad. Let's see. Could I plug in 3? 2 times 3 is 6. 6 minus 2. 2 to the 4th would be a little off my graph. So maybe I'm going to try and go back the other way. You said 0 is maybe not what I want, or maybe not the easiest, but let's give it a try. 2 to the 2 times 0 minus 2. So 2 times 2 is 0. 0 minus 2 is negative 2 for my exponent. So that means I would have to flip this to 1 over 2 squared. Don't love the fraction, but this isn't a terrible number, and it's something that will fit on my graph. So this would be 1 over 4. So if my y is 0, my x had to be 1/4. I've got 3 points. I'm going to go ahead and plot these. So 1, 1, 1, 2, 3, 4, 2, and 0, 1/4. You can start to see the shape of our graph there. Remember, domain refers to our x values, range refers to our y values. My domain is going to be limited by my asymptote. So this will have to be x values greater than 0. Our range is not limited. We're going to keep going down forever. We're going to keep slowly going up forever. So my range would be anything from negative infinity to positive infinity. Let's take a look at number 8. Number 8, we've got a natural log here. If I see natural log, just like when we saw E, I'm probably going to need my calculator on this one to be able to do those E powers. Just something to keep in mind when you see natural log or E, remember that that's something I might need my calculator to evaluate. So I'm going to start by rewriting this. Oh, actually, I'm going to start with my asymptote. Since this minus 1 is not in parentheses, that means it's not part of the argument with x. So my asymptote is still at 0. I'm going to go ahead and put that on my graph. Now I'm going to rewrite this. So I'm going to start by getting the log by itself, so I can move the 1 to the other side. I get y plus 1 equals the natural log of x. Now as I rewrite this, since it's a natural log, again, the base would be e to the y plus 1 equals x. Again, we're going to pick stuff for y to plug in and solve for x. So that little backwards situation that we've got going on. Now, e to the negative first power wouldn't be terrible. E to the 0 power, if I get the exponent to be 0, that'd be okay. If I could get the exponent to be 1, that'd be okay. E squared, since e is like 2.7 something, that should be on my graph as well. So I'm going to go ahead and see what I should plug in for y. So if I plug in 0, that would make my exponent 1. If I were to plug in negative 1, that would make my exponent 0. And if I were to plug in a 1, that would make my exponent 2. So I'm going to choose negative 1, 0, and 1 here. So this would be e to the negative 1 plus 1, which would be 0. Anything to the 0 power, including e, is just 1. If I plug in 0 for y, this would be e to the 0 plus 1. So my exponent is just 1. E to the first, we know, is about 2.7. Again, you can use your calculator for that one if you need to. And then finally, if I plug in 1 for my exponent, I would have e squared. We did a graph when we first talked about e, where we graphed e squared. If you remember from that, e squared is about 7.4, but if you needed to evaluate that on your calculator, absolutely you could. I'm going to go ahead and plot my points now. 1 comma negative 1, 1 comma negative 1, 2.7 comma 0, and 7.4 comma 1. So 1, 2, 3, 4, 5, 6, 7, 1. There's my graph. Okay. Anytime you sketch a graph and there's an asymptote, remember your graph should never cross the asymptote, okay? And you should never be plotting points that are on the asymptote. My domain here, again, limited because of our asymptote. So we'd be looking at x values greater than 0. Our range is not limited, so we could have any real number from negative infinity to positive infinity. Questions for me so far on our graphs? These are some of the tougher graphs that we've done. Okay, there's kind of a lot going on here. That's why we're taking our time. Let's take a look at number 9. Now, we talked about number 9 a few minutes ago, and we said this is a problem where my asymptote is going to move because I've got a left-right shift here. Since my x plus 4 is in parentheses, that means I'm looking at a change to my x value, and this will move me to the left 4 units. Okay, so my asymptote will be 1, 2, 3, 4 at negative 4 over here. Again, I like to put that asymptote in first because that's my boundary and I know everything should be on one side of the asymptote. Now we're going to go ahead and rewrite this in its exponential form. Since this plus 4 is in parentheses with x, I'm not going to touch it. I cannot touch it because that's part of the argument. So I have to rewrite it out of that log form first. So this would be 5 to the y equals x plus 4. And then if you want to go ahead and move the 4 to the other side, so you can do all the work on one side, that would be fine. And now, just like before, I'm going to pick some values for y to plug in and see what I get for x. Now, here's an example where I probably don't want to use 2 for an exponent. 5 squared, 25, that's going to be way off my graph. even taking 4 away, 21 is going to be way off my graph. So I want to stick with things like -1, 0, and +1 for my exponent. And since y is the only thing for our exponent, that makes selecting our exponent, the values I want to plug in, I should say, for y a little bit easier. So we'll do -1, we'll do 0, and we'll do +1 here. 5 to the -1st power, -1st power, would give us 1 over 5 to the 1st, which is just 5. And then we want to subtract 4. So I have -4 plus a fifth. That would give me -3 and 4/5. So we're just above -4. Or just in front of, I should say, since that's the next value. If I plug in 0, I would have 5 to the 0 minus 4. 5 to the 0 power would be 1. 1 minus 4 would give us -3. And then finally, 5 to the 1st power minus 4. 5 to the 1st is 5. 5 minus 4 would be 1. So I've got -3 and 4/5. 1, 2, 3. So I'm just in front of my asymptote here, and then down at -1. I've got -3, 0, and I've got 1, 1. My domain, again, limited by my asymptote, but not numbers greater than 0 this time. Since our asymptote shifted down to -4, we can have any x value that is greater than -4. Our range is still anything from -infinity to +infinity. Our last graph for today is number 10. I'm going to start with my asymptote. There's nothing in parentheses with x here, so that means my asymptote doesn't move. It's going to stay on the y-axis when x equals 0. I didn't ask you to write an equation for the asymptotes here, but if I were to, x equals 0. I want to make sure I write that whole equation. Okay, just like with your asymptotes for our exponential graphs, write the whole equation, not just the number. And now I want to rearrange this so that I've got my exponential form. So I'm going to start by moving this 1 to the other side. I want the log by itself before I change forms. So I get y plus 1 equals log base 1/2 of x. We did see in our notes this special property about if the base of our log is a fraction, we could rewrite this as negative something. I'm going to go ahead and just work with what we have here. I'm not going to expect you to use, like, you don't have to use that special property as we saw in our notes. It works if you use the property to rewrite it as a negative. It works if you leave it as a 1/2. So I'm going to save us a couple of steps here and leave it as that 1/2. So when I change this to its exponential form, I would have 1/2 to the y plus 1 equals x. And again, we're going to pick some values for y to plug in and use them to solve for x. Y plus 1 is not a terrible exponent to have. If I plug in -1 for y, that would make my exponent 0, so that's okay. If I plug in 0, I'd have +1. 1/2 to the 1st power is not bad. I could plug in +1. That wouldn't be terrible. I could also plug in -2 here. Okay. I know those negative exponents, we have to do some flipping, but this time when I flip, I'm going to end up with a whole number. That's not so bad. Okay. So if I plug in -2 for my exponent, I would have 1/2 to the -2 plus 1. Well, that makes my entire exponent -1. So this just means flip this. So that would be 2 over 1. So my x value would be 2. When my exponent is -1, I would have 1/2 to the -1 plus 1. -1 plus 1 is 0. Anything to the 0 power is just 1. If I plug in 0 for y, I would have 0 plus 1. So that's just 1. 1/2 to the first power is just 1/2. And then 1/2 to the 1 plus 1 would be 2 for my exponent. So 1/2 squared means square at the top. 1 squared is just 1. And then on the bottom, 2 squared would be 4. So 1/4 there. Plot my points. I've got 2 comma -2. I've got 1 comma -1. I've got 1/2 comma 0. And I've got 1/4 comma 1. Notice our graph is flipped, right, from what I would expect from my other graphs. This one's kind of upside down instead of growing up this way, going down this way. But as we saw in our notes, that property with the fractional exponent, we could rewrite those logs with a negative lead coefficient. We know negative lead coefficients result in a flip, right, for our transformations. This shouldn't be too shocked. My domain still limited by the asymptote, so this would be x values greater than 0. My range, still anything. Even though this is flipped, this time I'm going to grow really quickly this way, and I'm going to grow slowly as I scoop up all those negative y values. But that's still anything from -infinity to +infinity for my y. Questions for me today on our graphs? Okay. The last question that we have at the bottom of page 39 gives me a point on a graph, and it gives me the function. So it says the function log base 2 of x plus 2 would have the point 6 comma 3. Now it wants me to find the inverse of that function and give a point on its graph. The easy thing here is to give the point, right? The inverse function would have the sort of swap point. So if I swap the x and y, the point on this graph would be 3 comma 6. If I switch x and y, I get a point on the inverse graph. And then if I actually want to find the inverse function, we're just going to switch x and y from the original. So I would have x equals log base 2 of y plus 2. And we'll rewrite this to get y by itself. Since I've got the log by itself over here, we can go ahead and swap it to the exponential form right now. So this would be 2 to the x equals y plus 2. And then my last step to get y by itself would be to subtract 2 from both sides. So for my inverse function, f inverse of x, I would have 2 to the x minus 2. Questions for me for today? We'll come back and revisit our graphing after we learn how to evaluate logs without having to rewrite them in that exponential format. But for today, for our graphing, we had to use the tools we have in our toolbox, which was rewriting.